Molly May, and she's a grad student at CU in physics. And she has been working, she joined our team this last summer, and started in the spring developing skills in being able to prepare herself to talk down at the legislature and talk on bills. And so she's building her knowledge base, and it's just been so fun because we just give her a subject, she builds a knowledge base. And we give her a subject, and it's just great. So it's good to have a good mind. And if you want to add anything else about your background, that you could.
No, thank you. Great. Well, thank you all for coming. I really appreciate it. So as some of you know and was referred to earlier, Clean Energy Action has quite a history of building knowledge surrounding coal supply issues and price issues, which is kind of a different take than a lot of groups have. And pretty recently, just in the last month or so, I've become interested in similar issues, but surrounding natural gas, because it seems like that's a very quickly growing industry in our country. And I wanted to just kind of understand some of the different sources and the different takes on those issues in the field of natural gas. So as I said, thank you for coming, and I'd like to make this kind of a community discussion. I'm by no means an expert, as many people in the community are. So I'll give a little bit of background. I'll kind of divide it into 3 sections, my presentation. Start with just a little bit of background on what is natural gas and some general topics, and then after each section, I'll open it up for questions and comments. Then I'll get into just a couple slides of more detail on production issues and then price issues, with plenty of time for a discussion in between. Great. So just a little background on what natural gas is. It's mostly comprised of methane, which is a simple molecule, just a carbon with hydrogen atoms surrounding it. But as it's mined, it often has contaminants, which can take many forms. But heavier hydrocarbons, and then also things like hydrogen sulfide, which can be dangerous, and then carbon dioxide is often a contaminant, and even just water vapor. And those contaminants are removed before the natural gas is burned to create energy. Oh, I keep hitting this twice. So there are many ways that natural gas can be mined, but just to kind of get us all on the same page, I wanted to talk about some of the different methods. So the conventional gas drilling targets natural gas pockets that are one cohesive pocket, and it's kind of the straightforward way you'd think of to mine gas. You drill a well, and it flows easily from the well. So that's why this is called conventional gas drilling, and that's historically what people kind of started with. But something that's grown a huge amount recently is referred to as unconventional natural gas production, and that targets natural gas that's trapped in permeable rocks like shales. And this is the main unconventional method of producing natural gas is fracking, or hydraulic fracturing, which uses a high pressure liquid to fracture shale or other types of rock, sandstone for example, and allow the natural gas to flow from it. So over the last couple of decades, we have moved in the US from largely conventional natural gas production to a large majority of hydraulic fracturing. You probably already know this, but some things that natural gas is used for are heating houses, cooking. We can generate electricity with natural gas. And then a couple of lesser known things it's used for are vehicle fuel. And it's often used as a feedstock, a chemical feedstock, to actually make other chemicals. So you can change that simple molecule into more complex molecules, like fertilizers are one example, or plastics. And just to give you a kind of ballpark number, just so you have something in your head when people are talking about natural gas, the US uses almost 30 trillion cubic feet of natural gas each year, or this was the number in 2015. It's actually growing at about 2% a year. So natural gas is measured in cubic feet because it's a gas, so it's just measured by volume.
What percent growing?
2 to 3% is what I've read. Yeah, so about 30 trillion cubic feet in 2015 is what was used in the United States. And the Energy Information Administration, which is branch of the US government that does a lot of analysis, predictions, and just gathering of historical data for all sorts of energy issues. In their 2016 report, published that they predict domestic production to just keep going up, throughout 2040, and they expect us to become an exporter of natural gas as opposed to an importer. That's just what this consumption, which is the red line, versus supply, which is the blue line, kind of shows. So another thing I just wanted to touch on, because I hear it a lot in mainstream media, is this idea that natural gas can be used as what's called a bridge fuel. And so my understanding of why people suggest this idea is basically because per unit of energy produced, it emits about half as much carbon dioxide, or carbon dioxide equivalent, because methane is the relevant greenhouse gas here, as coal. Yes?
Is this slide just when it's burned, or is this the whole production cycle?
So yeah, that's a good question. Oh, sorry, yeah. So the question was, does this number refer to just when you're burning it at a natural gas power plant, or does this give the whole lifetime? And my understanding, I can check with you for that, but is that this does take into account the whole lifetime. But as I'll refer to later, I'm not sure that the EIA actually knows the number for the entire lifetime very well. So this is trying to take that into account. And so a couple of the reasons that it's better or cleaner burning than coal is that natural gas has a higher energy content, and also simply because a lot of natural gas turbines are newer than a lot of coal plants, so they're a bit more efficient. So there are a couple of issues I want to talk about as far as the global warming impact of natural gas, and why I think that the number for the whole lifetime emissions associated with burning natural gas for electricity or heating or anything is not necessarily a well-known number. There are two main subtleties that I'm going to talk about that I don't fully understand, and I don't think that our society fully understands. And the first one is the question of how do we compare methane, which is one molecule, to carbon dioxide, which is a different molecule. And both of these molecules cause heating of the atmosphere. They're both greenhouse gases, but they're different gases. And they're different in two main ways. The first important difference is just how effective they are at trapping radiation and heating the surface of the Earth. And methane is much more effective at heating the surface of the Earth than carbon dioxide, just molecule by molecule. But methane has a much shorter lifetime in the atmosphere than carbon dioxide does. So that's what this plot, which isn't showing up very well, I apologize, is showing, that methane is depleted from the atmosphere very quickly compared to carbon dioxide. So if we want to just produce one number to compare carbon dioxide and methane, this is usually referred to as CO2 equivalent, the equivalence factor, so that when I want to show you a plot like this, I can just give you one simple answer. We have to think about over what time frame we care about the warming of how much warming happens. So historically, the institutions like the EIA looked at several different time frames so that you could compare the heating of the two over different time frames, because there's no obvious answer as to what's the most important time frame. And so historically, they would publish numbers saying over the first 20 years, methane heats the atmosphere 86 times, and these are there's a little bit of disagreement within the community on these numbers, but methane heats the atmosphere about 86 times as much as carbon dioxide. But if you look at a longer...
Molecule for molecule, or atomic weight for atomic weight?
Okay, that's a good question. I don't know. I'll get back to you on that. Yeah, this was actually surprisingly hard to find the radiative forcing of each. But the idea is, so then they would also calculate if we care about a 100-year time frame. So over this time frame, carbon dioxide lives longer comparatively. So methane is only about 32 times as bad. And they used to calculate also a 500-year 8-year time frame. And I believe the comparison then is 8 times as bad. And then at some point, as I look back in the history of EIA data specifically, because they're a huge source on this stuff, they just kind of start reporting a 100-year time frame. And they just picked that, from what I can understand fairly arbitrarily, as the relevant time frame over which we care about how much heating occurs from methane compared to CO2. And I'll show you a little bit later that I think that's a problem, because if we look at the 20-year time frame, that's almost 3 times as much heating. So that would greatly change this plot, this number, that somebody might find easily on the EIA website and not really realize that there's any ambiguity there. So the other question that I think we don't have a great answer to as a society is, what is the full lifetime that you were referring to of effective natural gas? And that includes not only when it's burned at a power plant, which is a relatively easy number to calculate or measure, but also we have to include as it's mined, gas can be leaked into the atmosphere, and as it's transported through pipelines that go for miles and miles all over the country, any small leak can be just constantly emitting methane into the atmosphere. And that's a particularly difficult number to measure, because it's a very extended source, so you can't just put a little meter any one place and measure how much methane's being emitted. Yes?
Can I have you back up just a
Sure.
second? Because I want to clarify one thing. Back up the-
On the last slide?
Yeah. The global warming potential of the CO2 and methane, that's assuming the methane's not burned.
Right. This is emitted, methane emitted as a whole
Emitted just
molecule.
out.
Right.
So when you go
That's
one
right.
more back, that's assuming that it is burned, the emissions of CO2, not methane emissions on that.
So my understanding, and I might be wrong on this, but I have another slide that will kind of break this down a little later, is that there are some emissions of carbon dioxide, some of methane, and some of methane that are associated with using natural gas for energy. That's my understanding.
I think the dominant thing, it's just, you can't necessarily multiply that.
Right.
two to
That's
one
a good
by the
point.
other.
Yes.
And I just want to be
Yes.
clear.
They wouldn't
Yeah,
necessarily
it's
make
putting
this
natural
3
gas
times
in,
higher.
but I just
So what
didn't
he's,
want to
yeah.
let people get a wrong
Yes.
impression.
So what he's saying, just to be clear, is that this isn't all methane. Some of this is carbon dioxide, or is carbon dioxide.
It's graph of carbon dioxide only.
It's carbon dioxide equivalent. So this is,
I don't think so. I think that graph is CO2.
Yeah.
okay, well,
The other one-
That one metric I've seen before, and that, I wouldn't bet any money on this, honestly.
Chemistry.
But I thought I saw a combustion emission of CO2 from the two fuels without considering the whole product, before it gets to
Okay.
combustion.
so I have a slide that actually
Range of 1 to
breaks down all of the emissions, which is the next slide. So we can look at that for more specifics. But that is a really important point, that it wouldn't necessarily multiply this by 3. It wouldn't necessarily do
that's what I
that.
wanted to-
Yep, that's a great point. Anyway, so this equivalence factor is something that I think deserves a little more thought than it's given. And then also this question of what are the real leakage rates through natural gas pipelines? That's a huge, huge question. And there's one analysis that I personally really like that was done by Robert Howarth, who is at, Cambridge? Anyway, Robert Howarth. And he did it in 2011 and found that there wasn't much information on these leakage rates. Nobody had done studies, or very few people had actually done studies to try to measure these in any way. And so he kind of published a call to action saying, we don't know this number, and we should probably figure it out if we're going to be increasing our natural gas consumption a lot. And so a lot of people did some research. Like I say, it's still difficult to do because these natural gas pipelines are very extended sources that could have a leak anywhere along them. And so it's not possible to necessarily measure each point individually, or it's not economically feasible right now to do that measurement. But he compiled all this data then 3 years later in 2014 that was published after his call to action. And he found that about 2.5% of the natural gas was leaked from pipelines, and this is also processing facilities
Does that include leakages at the wellhead?
So this was just processing and distribution facilities. I can show you his paper had analyses of the other sections, but this is the one that I think is not well known, as less well known. Especially I think because it's these extended sources. The wellhead at least is one site, and you can do measurements at that site. That's my understanding.
So does this include the wellhead, or is it just?
No, so this
the
is
wellhead?
processing and distribution. Mm-hmm.
Looking at the two citations, which are a little confusing, I'm not sure that the numbers are right on them. One is from 2011, one from 2013. Have those leakage rates changed? Has technology cut back on leakage?
So that's a good question. And one of my main questions for you, or in general, is that I don't think we know that. So looking at scientific literature is a huge job. There's a lot of stuff to look at. But from what I've found, I'm not super satisfied that we know that. I don't think there's been a lot of technology specifically developed to fix leakage from distribution systems, because like I was saying, that's a very difficult problem. And just identifying where the leaks is a difficult problem. So I haven't seen a lot of movement on this specific issue. So this is the graph I was talking about that actually breaks down. Oh, so Howarth's, So Howarth's paper also kind of goes into this analysis that says, let's take into account the fact that 20-year time frame might matter, as well as a 100-year time frame. So that's what the top graph versus the bottom graph are. And then he also says, let's just, to see what would happen, use my number that was found by more recent scientific studies than the EPA's number. And then let's go back and compare shale gas, conventional gas, and coal. And he finds that, so to be clear, orange and blue are CO2 emissions, and pink is methane emissions. And so he finds that if we look at the two different timescales, there is a huge difference in the ratio between the emissions from natural gas and coal, partially because this methane emission is amplified if you use the 20-year time frame. And then also because there's this question of what are the true emissions. And so when you see numbers like this that are just published by the EIA, a source we should trust, and people saying we could use natural gas as a bridge fuel, I think it maybe takes a little bit more thought. Mm-hmm.
The slide that you just went back to, I looked it up, and that's just from combustion. It has nothing, doesn't have none of the leakage or any of that stuff.
And thank you. And does it have to do, is it just the carbon dioxide equivalent or just carbon dioxide? Yeah. It's CO2 equivalent, okay. So that was CO2 equivalent.
No, it's just the carbon dioxide.
It's just carbon dioxide. Okay, thank you. So that's not a very good number then.
It's combustion. They will have looked at.
They'll look at CO2 equivalent.
Combustion and the rest of that.
Yeah,
So a little bit
I
of,
think it's
after
CO2
the
equivalent.
combustion site, you're gonna
Yeah.
get a little bit of methane now.
I think it's CO2 equivalent, but it's just the combustion. Okay, that's great. Yeah, thank you. Mm-hmm.
I don't understand why there would be so much pink if it's just the byproduct of the combustion. If you burn methane, there's no methane left.
So this includes both the combustion, but also any leakage that happens at the wellhead and in transmission. So this does include the whole lifetime. That's correct. So these specific numbers,
And that's,
yeah, in the different global warming potential.
did you do the second one down on 20 years, or did he?
He did, so the bottom one is for 100 years and this is for 20 years.
So this is all 20 years, the upper one.
The upper one is different. I put a big text box over it so you could read this, but this is shale gas, and these are the low and high estimates because in his analysis, he says we don't know these numbers very well, so he does.
Talk while Molly's talking.
Oh, yeah.
Thank you.
So shale gas is these two, the low estimate and high estimate. Conventional gas is these two, low and high estimate. And then coal is these two. And then the last one was diesel oil.
Okay, so we have a case there where it's saying the high estimates, for instance, it's double the impact over 20 years than conventional coal.
Yep,
Roughly
that's
40,
right.
60.
If you take Howarth's numbers and if you take the highest estimates from what we know right now for leakage rates, which, like I say, I don't have a whole lot of faith that we know the leakage rates based on just reading a lot of different literature that finds some numbers said certain sites had 100 times more leakage than the EPA predicted, and some had less. So this is just something that I think we need to look at a little more carefully if we're going to be expanding our natural gas production a lot. Were there other questions on this slide?
But your point with the slide is that the methane, it has much more toxicity 20-year time frame.
Yeah, that's one of the points.
Figure all the other factors.
It's just another time frame that we should think about. And then this is just a quote that I found striking from the abstract of this paper, where Howarth says both shale gas and conventional gas have a larger greenhouse gas footprint than do coal or oil. He just kind of states his findings. If you take into account the 20-year time scale and the leakage rates that we now think are probably the most accurate, it's actually probably worse than coal. So we've been discussing as we go, but I'd like to just step back at this point. That was kind of my background review, and see if anybody has any questions about things that we talked about. So we talked about different mining methods, different little bit about usage rates, and a little bit about the greenhouse gas footprint of natural gas.
One element that might be missing here is outdated delivery pipes in cities like Boston, where natural gas used for cooking and heating escapes
Oh, interesting.
In massive amounts.
So this is distribution to the home, that
Right.
the lowest
So
level
the-
kind of
but
distribution.
methane all the same.
Oh yeah, definitely. It's just gonna get a drink of water. Yes.
Back to your very first slide where you showed the picture of the different technologies, the different ways of mining.
Go back there.
There is an amount of natural gas that's produced during the drilling for oil
Right.
that then gets lost, flared or whatever. So
Hopefully flared.
how much of that is happening?
That's a number that I don't actually know. So some of the analyses I read. Okay, yeah. I mean, I don't actually know that number, but I could write down that question and get back to you on it.
The number exists. I know the oil
okay.
and gas industry has,
let me write this
has
down.
put a dollar figure on that.
On if they.
on how much is basically
Okay.
lost through flaring. Because there would be a third, which is you're drilling for oil, but also maybe getting some natural gas and losing natural gas.
Yeah, that's a really good point. So those specific leaks are something I've been interested in. I think this is just kind of a guess. So a lot of the sources that talk about are the sources that we get natural gas from will specifically mention how much we get from this coal bed methane. So that's methane that is captured as we're mining coal in kind of a similar way. And they don't, or the ones that I read didn't actually mention methane that's, because I guess we don't capture the methane associated with oil drilling maybe.
Think about North Dakota or
But I'm guessing it's got to be less than the coal bed and maybe not a significant amount to capture. But as far as emissions, it could be a significant amount. And I hope that this study that Howarth did tried to take that kind of stuff into account as best we know to get a more lifetime number.
We know how much CO2 has increased during the Industrial Revolution in parts per million. Do we have, or do you have charts that show the same thing for methane?
Oh, that's neat. Like parts per million of methane in the atmosphere, basically. I don't have that chart in this presentation, but I did read that number. I think, yeah, so some of the studies that do, like the Howarth study, but some of the ones he used to try to understand the true emissions from natural gas pipelines, did that type of study where they would fly an airplane over large areas and measure the parts per million of natural gas in the atmosphere. And I think they tried to measure how fast that's growing, but I don't have that graph. But I could get back to you on that. That's an interesting question too.
The global
Or
averages
methane.
are measured, and the chief monitoring is right here at the middle of Martin Voelker.
Mm-hmm.
But they measure those on, Mount Dora, the same as they do the CO2, the Keel curve, and so on. It's a much smaller number, right? It's not ppm. It's
Yeah, parts per billion or something.
global averages measured.
Yeah, that's definitely a number that exists.
I don't think everybody can hear that.
Oh, yeah, so she's just saying, yeah, that it's definitely been measured, the number for how much methane is in the atmosphere as a function of time, basically, like each year. But I don't have that graph. Yeah, that would be interesting, though. I'll add that next time.
It's gotta be a hockey stick, right?
It's probably, unless the background levels were high. That's what I don't know, is like before the Industrial Revolution, I have no idea how much methane was in the atmosphere, but we've definitely added to that baseline.
So one thing that's never captured in any of these numbers is the impact of potential feedback loops in climate change, where putting a certain amount of heat, capturing a certain amount of heat in year one is not the same as capturing the same amount of heat 20 years out, and has a sort of exponential relationship to that if you consider that perhaps there are other mechanisms we're triggering, melting of ice, methane release in Russia, Russian tundra, and so forth. These are things, so when you put 100 of heat now, it has borne fruit by year 20, if you will. So when you accelerate on any time scale that you use it 20 years or 100 years as your benchmark, if you use 100 years, mathematically, by having the methane impact that's front-loaded versus the CO2, that impact is going to, a simple way to view this is financial analysis with interest rates having a compounding impact over years. I don't know how that could be captured in figures, but
I wonder how well we know that, how well we know how fast the interest is, how much the interest is.
From the IPCC.
For like over the entire globe, including melting of ice and tundra and everything.
We've done modeling of feedback loops,
That would be interesting. So if they did have a number for what that interest rate is, you could look at the 100-year time scale always, but include the feedback, and maybe that would be more accurate.
If I may maybe answer that, I think the issue here is not so much the compounding of the interest, but that we're close to hitting points of no return in those 20 years. That's why the 20 years count. That's why we shouldn't look at the long time frame as much as the key time frame, which is the next 20 years.
Right.
And the one thing that maybe hasn't been said yet is methane has a very short lifespan. And so for that reason, there's less compounding also, unless we keep pushing out more and more methane.
Yeah. I have seen some analyses that try to think in terms of how close this will push us to some of those like 2-degree warming or some of those kind of hard caps. So that's another totally different way to look at it, is just how much will it affect that. Okay, great. Well, the next thing I would like to talk about, if nobody has any other questions or comments, is this is just a more brief section, but some thoughts I had surrounding natural gas production. And I've seen this, again, in the media quite a bit, this proposition that we have 100 years of natural gas to use. And I wanted to do a little bit more background research into whether this was true or what all the sources say. So just to give a little bit of historical context, this plot shows natural gas withdrawals in several different regions within the United States, and then the United States as a whole. And in a couple of the regions, including Colorado, I think it's striking how much natural gas withdrawals have increased over the last 5 years or the last 15 years or 20 years. So these plots are kind of what started me thinking, is this sustainable? Can we just keep withdrawing natural gas every year? So the kind of first calculation I wanted to do was thinking about natural gas resources and how much we have as a globe and how much we use globally. And so these are just numbers from the EIA, but the last good numbers I could find were 2014, so I know that's a little old, but but it'll give you a ballpark. So in 2014, the global usage of natural gas was 120 trillion cubic feet. So that was about 4 times as much as the US, which is kind of interesting. And then in 2014 also, the EIA predicted that we have about 7,000 trillion total cubic feet of natural gas that we're pretty sure we can recover. Proven reserves, the technical definition means that we're 90% sure or greater that we can recover these reserves. So if you just divide that out,
What price?
so they say economically recoverable. So they're trying to take into account changes in price, I think. So that would last us about 60 years, just as a globe. And if you take into account the fact that natural gas usage is growing by at least 2%, that's one of the lower numbers I've seen, then that would mean this will last us less than 40 years.
Does that 2% growth assume continued use of coal? You know, I mean, as we think about replacing coal with natural gas, won't that number go up?
Yeah, so this is taken from basically EIA projections, which take them as you will. I'm about to show some plots that make me think they're not that great. But yeah, so I think that takes into account, that's probably assuming a base of coal because we already have a lot of coal plants. But the EIA predicts basically no more coal installations, that most new installations in the coming years will be natural gas or renewable energy. As far as new production, or new generation, sorry.
I think it was 2014 that the EIA withdrew a previous assessment of the Monterey natural gas. And I think that, it may have been 2013, but I think it was 2014.
Okay.
And that was an awful lot, and they cut it down by 90%.
So, yeah, I have
So
a slide
the
talking about that
69
next.
Maybe down to 55, but still 55.
Yeah, so this was just kind of, just an idea, ballpark numbers.
And it shows that they are very loosey-goosey when they first put them out, if they come back and cut them 90%.
So let's keep going to this slide. So this is getting at that exact same point. This is the Marcellus shale, but there was some analysis done by David Hughes, and basically he just wanted to look at this exact same question. What does the EIA say? Are there any other sources that have ideas about how much natural gas we have as a globe? And one of the things he points out is that the EIA has actually done this many times, greatly reduced their expectation of how many natural gas reserves we have. But this plot just shows one that was actually from quite a while ago. It happened in 2011 after the USGS published a report that was done based on data that they had actually collected and analyzed that was kind of probably right. And the EIA, after reading this report, was kind of forced to reduce their predictions of how much natural gas was in many different plays. But he picked 2 of the more extreme ones. And that's the Marcellus shale play. They had to reduce their previous expected amount by 80%. And then the Poland's natural gas resources, they had to reduce their expected by 99%. So Hughes did a little bit of digging into why this happened and what are they basing their predictions on. And he found some things that I thought were notable. One of the things he found was that an EIA official admitted that they based some of their numbers on presentations that fossil fuel companies had given them. So just PowerPoint presentations given to them by a fossil fuel company, and that's where they got their number, and they published that. And then, so he did some more digging, and he basically found that the models they use are not transparent at all. They're very difficult to understand, and they seem to make some assumptions that are very questionable. These are 2 examples. They seem to assume that we're just going to keep discovering new natural gas plays, so new resources, at very abundant resources that we have no idea they exist now. Which maybe that's true, but it's kind of a big assumption if you're talking about like the grid, the stability of the grid in the US. And then they also assume 74 to 110% recovery of reserves that we already know about. But some of these are classified as not proved reserves, but probable reserves or possible reserves. And some of them have only a 10% chance of being recoverable. So
You
the
mean economically recoverable?
economically recoverable, and technically too. So I'll get into a little bit more on the next slide, but they look at both, can we physically get this with the technology we have now, and is it economical? And not all of the reserves they refer to, but some of them only have a 10% chance, and then they seem to assume very high recovery rates from these questionable plays. So anyway, I don't really know, but I thought this was kind of an interesting thing to think about when you're looking at predictions published by the EIA is, can we trust this? I don't know. And then another source that's often cited when you see this 100-year supply of natural gas number is called the Potential Gas Committee. And so I did a little bit of research into their publications and where they get their data from. And I found kind of a similar thing, which is that over 50% of the resources that they're referring to when they say that are classified as either possible, which that's that one that has to have 10% chance of being recoverable, or speculative, which I couldn't even find a technical definition of, but my understanding is that it's exactly that. They're totally speculative, and they don't have to have any surety that these will actually exist. So that was a little scary. And then I looked a little bit deeper into their website and their publications to try to understand, what data they were using. Was this USGS research? And I couldn't find any sources other than themselves that they were citing. They specifically said that some of their sources are confidential because they work closely with E&P and gas pipeline companies, and those guys aren't willing to publish their data. So it seemed like there might be a conflict of interest here, and I wasn't really convinced in a scientific way that they were correct in saying that we have a 100-year supply of natural gas. Go ahead.
There's also a historical reason not to believe these figures, because the oil industry has been shown to do exactly the same kind of speculation for price political reasons.
Oh, interesting.
Yeah, they manipulate the supposed availability of resources in order to protect their pricing.
Huh.
And I will just reinforce that with another dimension on it. They do it so they get investors to invest in the drilling, and so it's really false investment information.
Right. And another thing that worries me as a ratepayer to a utility is, what are public utilities commissions basing their investments on? When they decide whether to build natural gas or coal or renewables, I just want to make sure that we have good information to base those decisions on. And it seems like even the EIA, which is kind of the sanctioned government information, doesn't seem that reputable. And another this comment, I think it's kind of irresponsible reporting as well. I see this number in mainstream media, and it seems like most people just aren't really doing their fact checking, which can be dangerous too, because just public information. So just to kind of add on to that, why I'm hesitant about this or worried about this, the Union of Concerned Scientists did a kind of interesting study where they looked at are different states at risk of being over-reliant or becoming over-reliant on natural gas. And just one of the plots in this publication was this, and the takeaway from it is that 26 US states are putting more, or in 26 states, more than half of the new power plants being built will rely on natural gas. And that's from, I think, 2014 to 2017. So we're becoming more and more reliant on this fuel source as a country. And I just want to make sure we aren't doing it being blind to some of these issues. So with that, I don't know if there were any more questions or comments on that section. We kind of stopped.
That last slide up again.
Sure.
So if I understand well, Molly, if you, where you calculated 40 years of reserves with a 2% usage growth annually, if you applied that, if you took out some part of the half of reserves that's either possible or speculative,
So to be fair, that EIA number was not the same as the potential gas committee number.
What was their number, do you know?
Their number, it was much bigger. It included that number from the EIA.
Okay.
That was the proved reserves.
Proved.
Those were
Oh, wow,
EIA's
the
number for the
12%
proved.
Okay.
Yeah, that's the part that the EIA actually condoned. So this one's just wildly speculative as far as I can tell, compared to even the EIA estimates.
Can you go back to the map?
Yes.
The last statement, 26 states, more than half the power plants are natural gas. You're not necessarily, though, making any kind of value judgment here, because one could say it's better, one could or could not say
Excuse me.
they would otherwise be coal.
Sure. No, I'm not saying that at all. This is just kind of backing up my intuition that the U.S. is becoming more and more dependent on natural gas. That's really the only takeaway here is I kind of had been hearing more about it, but this is kind of a number to show, yeah, we really are investing in it a lot. You're first.
So becoming more dependent at the same time that we are planning to start exporting it for the first time in how
Yeah,
long?
that's right. So yeah, that's true.
The phrase high risk is high risk vis-a-vis alternative X, Y, and Z, where it is higher risk compared to solar and wind, where we will have a continued supply. But it's maybe lower risk compared to coal, where we're already in deep doo-doo.
Yeah.
So the phrase high risk really is begging for a versus.
Compared to what else? That's a really good question. And so their analysis was taking into account a few factors. It didn't specifically compare it to coal or renewables. It was just pointing out a risk. And theirs was based not only on supply, but also on price volatility, which I'll talk a little bit about in the price section. And then if there were a potential price on carbon put in place in the future, would that change the economics of these investments? So that's kind of what they were basing this high risk analysis on. But for these purposes, I just wanted to show you that we really are becoming more dependent on
To
it.
his point, the term over-reliance is potentially
Leading or,
whatever,
Yeah.
yeah, good point. So this is just their title of their publication, but that's a good point. I mean, and maybe they aren't over-relying. Yeah, Laura?
The graph that's really striking, proving the same point, is just the total fuel or energy sources in the US for the energy we use, and the evolution from today through the next 20, 50 years from the IA, where we see, I think it starts a little bit in the past from today, but it shows that definitely the dominant fuel was coal, and what they're projecting is the dominant staple fuel
Yeah.
is natural gas. So that kind of states.
I
how
think I have
reliant
that in
we're
my
going to be.
supplemental slides. Yeah, I was trying to decide whether to do that or this, but yeah. So you can kind of see from a number of ways that we're really growing in our usage. Whoops. So did anybody else have any comments on that before I move on? Okay. Okay, great. Oh, yeah.
I was just going to say, it's not just an intuition that the switch to natural gas is massive. Pretty much all coal plants are being converted quite quickly to firing natural gas.
Right.
Because it's a price issue. So.
Yeah. I mean, the EIA predictions and even just what's happening this year is there's basically no coal. New plants, at least. No one's putting in new coal at all.
Yeah, but that's
Yeah.
artificial.
Yeah.
Economically dependent. I mean, there's tons of coal, and coal would be the cheapest if the Saudis were putting out tons of oil and we weren't fracking to high heaven.
Yeah.
I mean, the
But fracking is real.
industry is not doing well because the competition is so tight right now that they can't make money, but at the same time, they have to sell their gas, quite cheaply, So there's economic factors here that are really controlling the price, and if they weren't in effect, coal would be cheaper.
I would just like to say that I'd be happy to talk to you about that, and we could provide
extractable coal is a huge supply and that the future is for cheap coal and we.
Well, I didn't say that.
Oh, okay.
Well, I-
There's plenty of coal, but it's not accessible, at the risk of stating the obvious.
I think we're actually going to touch on the same issue, and maybe it'll kind of clear this up, or at least start a new discussion on it. So the last question I wanted to answer is, how long will natural gas be economically attractive? And what are kind of issues surrounding supply, or price, I mean. So just to give, again, some historical context, this is just a plot of the price of natural gas over the last 2 decades. And as you can see, we're kind of at a local minimum here, or a low point at least.
Are those
Sorry.
real prices or?
That's the real prices from the EIA.
Those are nominal prices.
Oh, I don't know,
Those are
actually.
averaged over
That's the Henry
months
Hub
Or years, whereas when. you get
natural
to the
gas
next
spot
one,
price.
You'll see the peak in this.
That's not the question. So that's
Adjusted?
it's the title is the Henry Hub natural gas spot price if you go to the EIA website.
Nominal prices.
So I don't know what the standard reporting is there.
Maybe this 2016 in the middle there says these are all 2016 dollars.
That's a really good question, actually. I bet they did. Yeah, that's a really good point, actually. Yeah, good question.
And Molly,
Mhm.
do you know what was the source of those spikes in '05 through '08?
No. Yeah, no, I don't. Does anybody have a comment on that?
Go to the next slide, you see the spikes much.
Well, that's okay, but that's a different issue. The volatility is different. These are like large scale spikes.
Like the Russian,
Mhm.
the Russian embargo.
Yeah, I should know that, but I don't. That's a good question.
These are US prices, Henry Hub prices.
And these are conventional dominated
Yeah,
in the
right.
spikes.
Right.
The after the spikes is when the fracking came in.
Yeah, so that's a good question. Yeah, I'll look into that for the next time.
We see the impact of fracking on the price.
Mm-hmm.
But the take-home point is, who knows?
So anyway, yeah, one hard thing for consumers of natural gas is this volatility that you see. If you average over a year, it looks like this. If you average weekly, the price just spikes to much higher, to $15 instead of $9, and much lower as well. But it's really just unpredictable, and that actually creates costs for consumers of natural gas, and that uncertainty can be difficult to deal with. So that's
The daily chart, it hit $18
Mm-hmm.
if you go back to 2006.
Mm-hmm.
It did.
But don't the buyers of these things have hedge contracts that allow them to ride out some of those spikes?
They do, that's part of the cost.
But it's
That's-
those are not.
Yeah, that price will be built in.
Mm-hmm. So that's one issue. But another issue, which was kind of referred to earlier, was I thought this striking analysis by Arthur Berman, who was just looking at how shale gas producers are doing economically. And he found that not only are some of them in bankruptcy, whoops, I didn't mean to make that red, but if you look at the debt to cash flow ratio for these companies, so that's how much debt are they accruing versus how much cash is coming in, that number shot up by an average of 4 times from 2015 to the first quarter of 2016, which is when he was doing this analysis. And that's another indicator that financially, I don't know if it's actually economical to mine shale gas. Just a point of reference, somebody might actually have a better number than this, but at least historically, banks would start to call in loans and kind of say, we don't think you can pay us back if this number got over 2 to a 2-to-1 ratio between debt and cash flow. And as you can see, some of these companies are getting up to, well, the extreme ones up to 30, but even the lower ones up toward 5.
That's interest payments on debt?
So I think that's accrual of debt compared to cash flow. Does that not make sense?
It would seem to me that it would be a cash flow, an interest income on debt compared to cash flow for a particular year, as opposed to accumulated debt, which could, depending on your interest rate, might not be such a big deal.
Wow, I really should know this. I don't though, but we can look at it afterward. Or
My guess is,
yeah.
I mean, if you're talking debt to cash flow ratio, in this last point, you're probably talking debt payments to cash flow.
Okay, so payments on the debt?
And I would have thought it was aggregated debt, how much debt the company has.
That number would be much higher than this.
The total debt, yeah, which would be much, much, much higher than the annual cash flow. Okay, well, I'll check on that before people leave if they're interested, because that's really important. I'm embarrassed that I don't know that.
Are these companies majorly involved also in coal, or are they typically primarily focused on
So
extraction?
I don't know, the text around this graph said that he was looking at the major natural gas producers in the country. So I also don't know that. So another price issue, I apologize, this slide is really complicated, but bear with me, is also in the same analysis by Berman. He predicts that the price of natural gas will double by January 2017 because of this exact issue that, that natural gas companies aren't making money, their debt is increasing. And one major reason for that is that the price of natural gas is well below the break-even point, or the amount it costs to mine natural gas. So that's simply not sustainable. And so this kind of overly complicated graph is basically showing blue, which is comparative inventory, or basically our inventory of natural gas, and then the price in red. And his analysis kind of takes this idea that they mirror each other, and we're coming down off of a peak in inventory, and so the price is going up. So just another thing that I think utilities and investors should consider when thinking about natural gas is that we might be at a local minimum for the price. And this has started playing out even since he published this analysis. But the price of natural gas won't always be below $2 per million BTU. And we do need to consider that investing in a natural gas plant takes a long time to pay off. And we're kind of locked into buying gas for decades if we choose to make that upfront investment, that's how we want to generate our power.
Does he assume exports coming into play here?
So this is the blue numbers are actually from the EIA. And so that's just their aggregated, their inventory for how much they think we have. So I assume it does. And then the orange number is also the EIA number, which also predicts a price increase. He did his own analysis, which predicts a bit more extreme price increase because the EIA kind of assumes that production will kick back in faster or after the price increases.
So that inventory is storage? Is it? It's stored in tanks?
It's how much we have, but ratioed to the average of how much we had this day over the last 5 years. So it's basically, it's a ratio of how much we have now compared to how much we've had on the same day of the year in the past.
But that, how much is?
But it's an actual inventory.
Already pulled out of the ground and sitting
Yeah,
in tanks?
it's an actual
Or in salt
inventory.
mines kept.
Gotcha.
So I just had those two slides on price issues, which were kind of similar to the conversation we already had. But does anybody have other questions or comments on that idea? You want to go back?
Yeah, go back. So
This is good.
Maybe I'm being penny ante or just.
No, this is great. Yeah.
But so if he's saying that prices will double,
Mm-hmm.
and if you think about your supply and demand curves crossing, so he's saying that basically we're going to lose supply, and so the price at which they can actually provide product at a profit is going to have to go up. But so there's, I wonder whether he's saying that this is going to be a stable price at double today's rates?
No, I think they predict, I think they kind of predict it'll keep oscillating as it has historically done. So this goes out to just through 2017, and even within there, his prediction
Right,
goes
'cause
up and then back
The
down.
moment prices double, your inventory is going to start going back. and then your price is
And
gonna
the-
go back
yeah.
down.
It's definitely a cycle, yes. But it's just to show that you can't just take the price it is now, which is a local minimum, and say, what if it's this forever, and then we should make this investment. So, but yeah, it's a cycle.
I get a newsletter that tells me about the number of wells being drilled, rigs involved, and then drilled wells but not completed, meaning they haven't done the fracking, so they have a well sitting there ready to frack. And the rigs in use right now are down something in the range of 75% because the price is low and declining. But and the things that they've drilled have not generally been completed, meaning they've put the high pressure stuff in frac. So they have a lot that are ready to give when the price comes back up. Because all of these are depleting, all the existing ones are depleting very rapidly. So they're ready to frac without having to re-drill, and they'll do that before they start to re-drill. So there's a few stages of prep to get the next stage.
Yeah, so it can't happen instantly.
But it's.
But they're ready.
They're part way into it.
Oh,
but
interesting.
holding.
Okay.
It's mama's at 8 months, but she won't get to 9 until they decide.
So if I'm off the mark on this question, and you want to talk about it outside of this.
That's fine, yeah.
Feel free. It's my understanding, or I've been told, that fracking has a very short-term return. That in order for it to work, that if you're going to fracture some shale today, you're probably going to get all that natural gas in a very short time period, and then you have to frack some more, and then you have to frack some more.
Because it depletes faster.
It
Yeah.
depletes faster, and so I wonder what you can say to that point. I mean, is there? The idea of there being a big pool of natural gas
Right.
underground and you just tap in and then you draw from it
Right.
for 30 years, is that different than the economics of fracking where every 6 months you have to go out and do more?
Yeah. Well, so it's I mean, anybody should feel free to make a comment because this is kind of just, I don't know a ton about this. But one reason I think people like it is because it's like a smaller upfront cost maybe, and then a quicker payout. So it's like a shorter investment time-wise. So that's one thing. And then that also reminds me of the production analysis. That's another mistake that Hughes thinks the EIA makes, is not realizing that fracking plays have huge depletion rates, like 30% within the first year, huge depletion rates. So that's another thing that's not really answering your question, but that isn't accounted for in production. But does anybody have other ideas on how that would affect the economics?
Well, the depletion is much faster than 30% in the first year. It's depleting a lot faster than that. And so when you look at these fields, they are depleting. And there's a couple of the major fields now that have experienced peak production in the U.S. that they would have thought would go further, but they have peaked out, even though they are coming back and re-fracking, and they've got the network out there.
Right.
So there are people that are saying in published journals that, or at least on the web journals, that we're really going to get to total peak natural gas by 2025 in this country, and then we're coming down. Because the conventional, you saw, already peaked a long time ago. That's why we had the price peaks in 2006 that were up in the $14 to $18.
Well, fracking has been around since the 40s, but it was never needed until
Right.
recently because the regular pools of oil.
There were conventional
gas
sources that are
supplied
cheaper.
gas and so that it didn't become viable until
Right.
recently.
Right.
I'll just say one more thing.
Sure.
The answer to the question, will it always be cheap? No, because we build up even more reliance, and we're going to be exporting, and we're going to be in a decline, and we have McMansions that are sucking it in. They're not well insulated.
Yep. That was kind of the conclusion I came to. Anyway, good. Well, thank you for coming. Feel free to ask or chat more afterward. But that's pretty much all I have.